drawings, where will I see them?
So usually it kind of pops up,
Okay.
but you want to keep an eye on this one. This is with admin. So all right, guys. Well, welcome to the fourth class. Today, you guys will be doing math and science, math with Aubrey. So I would like to introduce Aubrey. Aubrey is a teacher. We just hired her a few months back, and I can tell you she has one of the best teaching skills I've seen. I've had a lot of people comment about her, compliment about her math skills. So she'll be helping me, helping New Horizons starting this year with ACT Math, strictly ACT Math. So she has curriculum we have set forth for her, and you'll be seeing her quite a bit this semester onwards. Sounds good. Again, ask questions. She's great in explanation, and same with online students. Just make sure you ask questions. Don't hesitate. We're gonna go till 4:55. Have a 5 minutes break. Same routine basically, right? And then I'm gonna be here starting with science. Sounds good. Math or mouth and nose. I know it's hard, but that's what it needs. Sounds good. All right. Have fun, guys. Aubrey, all yours.
All right. So, yes, my name's Aubrey. I taught math for a few years. I've tutored for several more. And my first experience with the ACT was in 8th grade. My talented and gifted teacher said, go take this test. And I said, okay. And I took the test. I don't remember a whole lot about it other than you weren't allowed to read when you were finished, which distressed me because that was my default for standardized tests. You get to read, and so that's one of the most memorable things about the ACT was, oh, they really are strict. You can't do anything other than look at this test during the time. And got a 25. Didn't know if that was good or bad. I just, okay. And then when it came time, oh, thank you.
It was on mute, so.
Sorry, I was saying that my name is Aubrey, and I'm a math teacher, and got a 25 when I was in 8th grade, didn't know anything beyond, okay, I have a score. And then got up to college age and started caring, took the test again, got a 32. Again, I never did prep. That was purely based off of classroom exposure. And my scores were really super good except for English. My English test was horrific, and compared to everything else, like, oh wow, I thought I was good at the English language, but apparently not. And so I studied on that one a little bit, had the benefit of a great advanced composition teacher, and went back and took the test again. Got a 32 again. English score went way up, math score went way down. I forgot my calculator. I took the test cold with no calculator at all, still managed to get a 32 average, but between those two it always just irked me a little bit, but not enough to go back and take the test again because my mother's like, no, you've got the score, you're going into college, life goes on, don't stress about it. And so for this, I'm going to tell you one person can get a 28 and think, that's amazing. One person can get a 28 and think, I have failed at life. It's about what you want. All of this stuff is stuff that you will have seen in a math class. The question is whether you remember it or not. That's kind of there. But it's not terrifying. It's just getting familiar with it, getting comfortable with it, and not being intimidated by it. So that's what we're going to do today. Just as a show of hands, and if people online want to unmute and chime in, how many of you have taken geometry already? Okay. Most of what we're doing today is geometry, and so we're going to be going over that a lot. If it's something you've never seen before, sit back, absorb it. You're going to have that class before you take the ACT for college realness. It's just the way the classes progress. If you've seen it before, take it as a review and a reminder that even though geometry is that weird outlier class compared to all the other algebras, it's still there, it still comes back. All right, with that, go ahead and get started. We get to jump to page 1 in this lovely book. So So I'll give you about 2 minutes to read over that, and then I'm going to draw some things on here to work with. All right, so first thing to get out of the way is geometry very conceptual. On one hand, it's, yeah, we can draw it. On the other hand, they're talking about something with no width. How does something have no width and we're still able to draw it? So the easiest way to do that is here, I have black, I have white. There is nothing in between the black and the white. But that boundary, or that transition, is what a geometric line is really talking about. It's talking about there's this side, infinitely many points with no dimension, but there's that boundary in between the two. And the same way, we can imagine it going off forever in both directions. Geometry can get into the 3D world, but for everything we're doing, it's talking about plane geometry, and plane not as in boring, plane as in flat, like the Great Plains that we live in, which aren't quite as flat as plane geometry. So, first off, we have these lines going off in infinite directions. The arrows mean that it's continuing, and then segments are talking about pieces of this line. And so we can talk about the segment AB, the segment BC. It's talking about just this small section in between the 2 points. Points are always, going to be labeled with capital letters. And if you ever see something that looks like a lowercase letter, that's the variable meaning the measurement or the distance between these 2 points. And so uppercase letters are talking just, this is how we label that point. Lowercase are talking about the actual measurement or the distance there. And sometimes it'll be just a letter, sometimes they'll throw in algebra again and have something like 2x minus 3 for the distance. But that is what's going on there. So, again, how to label it. Capital letters. A means point A. If I say AB, it depends on what hat I put on top of it. If I put arrows, it's talking about the line that continues on forever and ever and ever. If I put, just the stick, then that's talking about just the segment just that piece. And if it says AB with no hat, it's talking about the distance between the 2 points. AB happens to equal M. So, angles, I suppose we should talk about one more line piece. If we took our AB and only put an arrow in one direction at it, that is talking about starts at A and shoots off forever and ever towards B. And that one's called a ray. You can think about it as rays from the sun. Anything that can help you know that it has a specific starting point, but then it continues forever and ever to infinity. So, when we get to angles, angles are made up of 2 rays. They have this starting point, and then it shoots off in 2 different directions. This one is going towards L and towards N. So, for reference, I don't know if it'll come up or not. This is called the interior, because it's inside the angle. This is the exterior, it's outside. Lots of different ways that they can label that, and they will probably throw all of them at you. The easiest one is in situations like this, it can just be called angle M, because this is what's known as the vertex, or the corner, or the starting point. We could label it with all 3 points and say L, M, N. We could go the other direction, N, M, L. And all of those work. Also, sometimes they'll put a number inside. And so this could be angle 1. The reason that we can't do this all the time is sometimes you'll have multiple things at the same starting point, and now M doesn't mean anything because there's this great big angle, there's this one, which one are we talking about? And so when they throw these multiple ones at you, it's because it's for clarity, it's more than one angle going on. The other thing to be careful of is, okay, so I just need all 3 letters. Why can't I say angle M, L, N? Got the 3 letters, but vertex is always in the middle. So angle MLN is actually talking about this angle up here. And so it switches what angle you're discussing. And so it's important to know the conventions so that you can put it into the drawing correctly. All right. So, acute, obtuse, right. From my tutoring experience, usually even people who haven't had geometry before, that got drilled into your head in elementary. Acute, he's cute, it's small. Obtuse, it's big, it's wide. An obtuse idea is a wide open idea. And right, it's right for building. We like square corners. They're all around us. Ceiling, floor, walls. Right angles are very integral to our society, and so we use them a lot. Straight, what does that sound like? Straight angle, straight line. What is its measure? How many degrees? 180. The ability to use that, really important. If you need to refer back to, okay, doing a 360 means somebody completely turned around, half of that is 180, go for that. But any way that you can remember 360 is a whole circle, 180 is a half circle, 90 degrees is a quarter circle. Those should be really at the surface of your brain because they'll be very useful. All right, last ones on this page are complementary, supplementary. I'm going to tell you them both, but you're going to have to come up with your own memory device on how to keep these two separate. Because if they tell you complementary angle and you use the wrong number, you've shot yourself in the foot to begin with. And at the ACT, they're tricky. They know kids are going to get those mixed up. They're going to give the wrong answer as one of those options. They're going to plan ahead and figure out that wrong answer and offer it to you. So, I remember it by alphabetical order. Complementary is C, 90 comes first. S, supplementary, 180 comes next. You can think of complementary, compliments make things right. Go for it. But find a way to keep those two straight. And if you're not 100% confident, use that as a studying thing because it's an easy thing to mess up. And when you do mess it up, everything falls apart on you. And it's just because of a terminology thing. It's not hard, it's just tricky. All right, so the two things that I predict you seeing with this is called segment addition and angle addition. So there's a whole bunch of geometry that they will do theorems and stuff when you're in class with it. But for this, you just need to be able to use it. And so if we take away the algebra, and I tell you this whole thing is 12 inches long. It's not because my drawing is not to scale, but I tell you it is, so it is. If I tell you this whole thing is 12 inches long, and this is 7, what's the length of BC? 5. You can do that just instinctually. You know that. If they throw algebra at you, just draw a picture, fill in the values, work with it. It's just this problem with different numbers. And so they will tell you, and they won't give it to you in the picture, they'll tell you that B is between AC. AC, B is between. If the measure of AB is x plus 4, and the measure of AC is 2x plus 8, find the measure of BC. Do you have any idea how you would set that up? So, what you are using up here is the idea that the whole thing, AC, equals the two pieces, AB plus BC. From here, it's filling in what you know. AB is x plus 4. AC is 2x plus 8. And here we get into algebra. What do you notice about our answer? Or rather, can I get to a number answer? No, we're still going to have an x. If we subtract x from both sides, we get x plus 8 equals 4 plus BC. And if we subtract 4 from both sides, x, 8 minus 4 is 4, x plus 4 equals BC. So, I apologize for my slanty writing, but AB, go back to our picture, was x plus 4. What's BC? X plus 4. So, since this was only in terms of x, we don't have a number to go back to. We found out it happens to be the midpoint. That's kind of cool. But it's okay to have numbers or answers in terms of variables. They will do that to you. They'll have you solve for a variable. They'll have an answer in terms of variables. It's not always going to be a number or an answer. You just do the solving the same way you always do. What comes out is very possibly the answer they're looking for. So don't freak out of, there's not a number. That's okay. Sometimes there's not numbers. All right. Questions on this? With the angles, it's the exact same. If I call this angle 2, it'll be angle 1 plus angle 2 equals the whole thing. We can call that angle PMN. And so, whether it's the segment addition or this, the two small pieces add up to the bigger piece. And if at any time you feel overwhelmed by that, go back to numbers. Say, okay, this is 35 and this is 20. What's my whole angle? Degree signs. One's 35 degrees, one's 20 degrees. Again, not drawn to scale. Yes.
55.
It's just 55. You add the two pieces. And so, if you need to give yourself a drawing because they didn't give you one, do a drawing. They give you space if you're doing the paper. They give you scratch paper if you're doing a computer version. Draw yourself a picture. In geometry, always. All right, next page, go ahead and take a couple minutes to look. And then we will move on. start this one, we are very quickly going back to the previous page and thinking about the idea of supplementary, or adding up to 180, making a straight line. And so if we look at our intersecting lines, this angle is going to be supplementary to this angle, because if we ignore this part right here, we have a straight line. Make sense? Now, if we ignore this part right here, we also have a straight line. And so this plus this has to equal 180. This plus this also equals 180. These are the same, because added to the blue, they both make 180, so they have the same measure. And the same way, red plus blue equals 180, so red plus blue equals 180. Anywhere you have them making a line, you add up to 180. And when they're across from each other like this, they're called vertical angles. Vertical angles are equal. And again, they love to mix together the geometry and algebra. So they're going to tell you, okay, you've got these vertical angles, one is equal to x, this, and solve. So, next step, slightly more complicated, they throw in, okay, you have parallel lines now. So we already know these vertical angles are the same, and these angles are supplementary to them, and also the same. If we imagine parallel lines, what do they mean? They're always going the same direction. They don't cross. They go in the exact same direction, and so they stay the same distance apart no matter how far off in the distance. They're never going to converge or come together at a single point. If we had these vertical angles really super close to, or if we had these parallel lines really super close to each other, to the point that they were, almost overlapping, we could see these angles are going to be the same. So, that's not proof. If you've gone through geometry, you know saying, well, imagine the lines are really close together doesn't work in T-sharp proof, but it does work for remembering the relationship that this angle is the same. And the instant you have this angle the same, you can say, okay, these angles are also the same because they're vertical, and these ones are also the same because they're supplementary. And now we've got a whole set of angles to work with. And so if you can remember the vertical supplementary and get one pair the same, you've got the whole relationship. In parallel lines cut by, this is called a transversal. To transverse something means to cross it. So parallel lines cut by a transversal, you only have two possible angle measures. If they give you a problem like this, there's only two different ways to set up the problem. You're either going to be using an equal sign, because they're two angles equal to each other, for instance, this one and that one, or you're going to be working with their supplementary, they add up to 180, for instance, this one and that one. And so the only thing you need to do is figure out which pair you have. Because again, if you do it wrong, they plan for that, they give you the wrong answer for if you don't set it up right. All right. Any questions on parallel lines cutting transversals? Again, if you've never done geometry before, I just went, woo, but know it's coming and it's not that scary. All right. So, perimeter and area. You can memorize the formulas. I don't remember what formulas they give you versus don't give you. I would have to look. They've got math facts and formulas in the back here, so I assume that they would be available on the test as well, but I'm not certain. So, perimeter. What does perimeter mean? Sure.
The total length of like the outside area of
Don't mix area. Total length of the outside distance. You can think about a security guard walking the perimeter of a building. A perimeter is the distance around the outside. So you're taking all of those measurements of all the distance around a shape, find that total length. So it's the total of all the sides in a circle. It's circumference, which is the distance all the way around the circle. It doesn't really have sides per se, but you still can find that measurement. Perimeter is the distance around. Area is how much is in the middle. And so, for a square, the perimeter is just adding up the four sides. And a square, what do we know about those sides? They're all equal, they're all the same, and so you can just multiply one side times 4. Or if they give you the perimeter, you divide by 4 to find what's one side. Knowing the relationship between those two is good. And then the area, again the most basic, length times width, they're the same one, so just a side squared. Rectangle. Again, the ones across from each other are the same. And so if you know 2, you can find the other 2 very easily. Or you can just multiply a side by 2 times 2, add them together. Length times width, same. It's a right angle, you just find the area. Parallelogram gets a little bit more interesting. What is the area of a parallelogram? This is sometimes referred to as the base. That'll come up a lot. And this is the height. And that's because if you chop this off and put it over here, it's just a rectangle. Also, triangles will be the same way. It'll be base times height, but then you just have to cut it in half. That's easiest to see with a right triangle. Yeah, the marker is going goofy. Because if we have a triangle, rectangle, and it's half of it. This sort of triangle is a little bit harder, but you can still see it. If you want to know about the weird slanty ones, why it works for this triangle, see me after class and I'll show you. But it's not worth the time now. Just trust me, 1/2 base times height works for triangles. Alright, so first and foremost, they have us reading about diagonals. What are diagonals in a shape? Do you guys know? So, any shape called a polygon, many-sided figure. I'll do a pentagon because it's kind of fun. We have sides. We can talk about the height, which is the right angle from the base to the top. But a diagonal is from any vertex or corner to another vertex or corner that crosses through the inside. That's what a diagonal is. And so on quadrilaterals, which are 4-sided figures, there's some useful stuff. If you have something with equal base angles or equal bottom angles, it's a bad rectangle, but if I tell you it's a rectangle, those two will be the exact same. If it starts leaning the way my drawing is, this gets shorter and shorter, that gets longer and longer, it's no longer square. Carpenters use that still when they are making door frames. They run strings to make sure the door frame hasn't leaned sideways. So, rectangles. Obviously, squares. Less obvious is isosceles trapezoid. So there's a word for you. You guys remember what a trapezoid is? It's going to have one pair of parallel sides. So the top and the bottom will be parallel, the other side's not so much. And if it's isosceles, then these base angles are the same. And so the diagonals of an isosceles trapezoid also the same. So useful. So diagonals bisecting each other. So bi, prefix that comes up a lot in geometry. Why is a bicycle called a bicycle? Two wheels. So bisect means cut in two pieces, specifically two equal pieces. Anytime something talks about bisect, it's been cut into two equal pieces. And so parallelogram these diagonals are cutting each other into two equal pieces. That's the same as that. This is the same as this. Also, square or rectangle, parallelogram, and then the rhombus, which is a squished square. All the sides are equal, but the angles are no longer 90. It's just sideways. And then diagonals bisecting at 90 or cutting each other in half at 90 degrees. This is not a 90-degree angle, obviously, but for square, assuming I draw it correctly, 90 degrees. A rhombus, again, equal sides, they will meet at 90 degrees. And then a kite, which looks like that, they will meet at 90 degrees. Kites are special because they have pairs of congruent sides, but they're right next to each other rather than opposite each other. So, we've got a couple minutes. Progression of how these work. Quadrilateral, four-sided shape. There are going to be straight sides, but there's nothing else special about them other than that there's four of them. But if we go to a parallelogram, now these sides are parallel to each other. So we've got those diagonals bisecting each other. We have parallel sides. We can find out all sorts of stuff about the angles from the parallel thing we talked about earlier. With that, remember, this works out to be that parallel lines cut by a transversal, and so you can always extend the edges and use those parallel lines. But, so, diagonals bisecting each other. We can go two ways. We could say, let's make all those angles 90. Let's straighten it up. And it can become a rectangle. Or we could say, let's make all the sides the same length. We have the rhombus. Everything that's true about a parallelogram, you can use with these two. And so knowing, oh, this is just a more specific case, this is still a parallelogram. This is still a parallelogram. It helps organize all those rules that you can use rather than trying to learn a new set of, oh, it's a rectangle. I can have this, 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 this. Rectangle. Oh, it's got 90-degree angles. Everything's true about a parallelogram. And so, finally, if it's both a rhombus and a rectangle, that's a square. Because we've got all the sides the same, and we've got those 90 degrees. so again, if you organize what properties you can use, it makes it a little bit easier to keep track of rather than trying to memorize everything for everything. Alright. I am talking an awful lot, so I apologize. Are there any questions? Don't feel stupid if you say, wait, you're going too fast, because there's so much stuff in here. I looked at this and I thought about teaching this in an hour, and I'm like, I can't teach. I can only review. So, they're throwing areas of trapezoids and kites at you. So, again, trapezoid, take it on faith. If you want to know why it's the case, I will show you, but that's probably not the best use of time. I just think it's interesting. Kites, it's a little bit easier. You've essentially got four triangles, because with the kite, they're telling you to take this diagonal times this diagonal and then divide by 2. If you took that diagonal by that diagonal, you'd be finding this large rectangle here. And notice this area is half of this space, half of this space, half of this space, half of this space. And so that divide by 2, you're finding the giant rectangle and cutting it in half. So, sum of sides on a triangle. This is something that I think you would find to be intuitive, or it makes sense, but maybe nobody has ever pointed it out to you before. If I give you a stick this long, and a stick this long, and a stick this long, and tell you, make it into a triangle, is that possible? No, because I mean, if you took this little one, and even if you tried to really stretch it, there's no way that's ever going to work. It cannot form a triangle. And so in order for a triangle to be possible, what this is talking about is the sum of 2 sides must be greater than the third side, or the sum of 2 sides has to be longer than the third side. You could have a really long piece and a really long piece and a really tiny short piece, because then you just have this tall, skinny triangle. But if you can't say any 2 pairs add up to bigger than the third pair, it doesn't work. It's not a triangle. And the same way, the sum of the triangle angles are always going to equal 180. And I don't have paper with me at the moment. It's kind of fun. If you cut any triangle out of paper, tear the corners off, and line them up, they'll make a straight line. It's just the way they are. And there are ways to prove it, but you just need to be able to use it. Any 3 angles of a triangle have to add up to 180. And so if they give you 2 angles, you can find the third one, because it has to equal 180. Right. Final words. Triangles can be categorized by their angles or their sides. And you can mostly mix and match those any way you want. So, what are some of the side words for triangles that you remember? This one's in the book, so. Side words to categorize triangles. got three options. The equilateral, you probably remember from elementary, says all the sides are the same. Isosceles has two sides the same and one different. And scalene, all three sides are the same. Isosceles has a useful property, and this extends to all the triangles, and we'll go back to that in a second. But if these two sides are the same, the angles across from them are also the same. And so if you have isosceles with the sides, what's called the base angles are also going to be equal. And so that can be really useful. If it's equilateral, again, it's also equiangular. All three are the same. And then scalene, they're all different. So, with those first two examples, what connection can you start to make? Here we had two equal sides and we had two equal angles. Here we had three equal sides, three equal angles. What connection can you make between a side length and the angle it goes with? Yeah. Was that it?
The corresponding angles and sides are the same?
Yeah, if the sides are the same, the angles are the same. And going beyond that, if we stop and think about it, I'm trying my best to draw these sides the same. But the wider an angle gets, the longer its opposite side gets. So as this is opening wider and wider and wider, this side length is also growing larger and larger and larger. And so sides and angles have this fun thing. One, don't always trust the pictures in geometry. They will say not drawn to scale a lot. But if we're assuming this is drawn to scale, and I call this A, B, and C, which one do you think is the biggest angle?
B.
B, because it's across from the longest side. The same way, C is going to be the smallest angle because it's across from the smallest side. And so those angle sizes will correspond to the side lengths. All right, so other angles with triangles, acute triangle has all acute angles, and that makes sense because it's acute, but obtuse how many of its angles are obtuse? Just one, because the rest still has to add up to 180. If you have two obtuse angles, not a triangle anymore, they're shooting off in different directions. And so for an obtuse triangle, one obtuse angle is enough. In the same way, this is an obtuse scalene triangle. They're all different. This is obtuse, but isosceles. However, equilateral, equiangular has to always be acute. I can't have an obtuse equilateral triangle. Last one. What type of triangle have I not mentioned yet? It's at the bottom of page 3.
Scaling.
Hmm? No, we talked about scaling further down.
Right angle triangle.
The right angle triangle. These are also just usually shortened to right triangles. And just like obtuse, one right angle is enough to call it a right triangle. The other two by default are acute because they only have 90 degrees left to split between the two of them. But Pythagorean theorem is what we're going to end on today for the last 5 minutes. And it's mostly written as a squared plus b squared equals c squared. It's the relationship that if you have a right triangle with the corners A, B, and C, the sum of the two legs, or short ones, or sides that come off the 90-degree angle, are going to add up to the square of the hypotenuse, or the longest side, or the one across from the 90-degree angle. So the way these A, B, and C come from is, if this is angle A, the side that's not part of making up angle A, the one that's across the triangle from it, is labeled A. The side that's B is labeled B. The one across from our right angle is labeled C. And so that's where that's coming up. A squared plus B squared. Does not matter a bit if this is B squared plus A squared. It's addition. Order doesn't matter. However, mixing it up with C completely changes our answer. So rather than just memorizing this formula, I want to take a couple minutes to talk to you about this. This is the hypotenuse, or the long piece. A and B, doesn't matter. Flip-flop them any way you want. Don't get stressed out of, oh wait, which one's A? And so if somebody gives you a triangle that says 3, 4, X, you're going to be using this formula. But which one do you put in for A? 3 or 4? Doesn't matter. It's just one of these short leg sides. So 3 squared plus 4 squared equals X squared. This one, I'm cheating a little bit. It's called a Pythagorean triple. It's one of the few numbers that works out to a nice, pretty answer. 3 squared is 9, 4 squared is 16, 9 plus 16 is 25. 25 equals X squared. X equals 5. If I don't plan ahead and I pick numbers at random, the chances of it getting to a nice, pretty answer, very low. Square roots are completely possible answers, very common. Unless they're contrived, you will most likely end up with a square root. Last question before I release you. If you learn one thing from me, if you are given this problem, I do not want to see 7 squared plus 13 squared equals y squared. Use the information that you have. This is the hypotenuse, the long side. This is going to be the one all by its lonesome. You will have 7 squared and then put in y for the b and have y squared there. And so you'll do a little bit of algebraic solving before you get to taking the square root. But use what you have and know what the formula means. Don't just say automatically, I have to plug in and then add up and then take the square root. Know what information you have. And that will help you on pretty much anything on this. Always know what information you have before you leap into the solving. Right. With that, I will let you take a break. Thank you for being a good class. And if you have any questions in particular, I would be thrilled to answer.